7.16, calculate these limits. And as you see, all of them are going to be the limit when x goes to infinity of something that involves 1 over x. Okay, and so what we are going to do is manipulate these expressions so that we can get them as fractions, and so that we get an 0 over 0 indetermination, or infinity divided by infinity, and so that we can apply L'Hopital's theorem. And we will also apply change of variables to get rid of this 1 over x. Okay, so let's start with the first one. So this is the limit when x goes to infinity of x times, and then 1 plus 1 over x to the x minus e, right? So this is x is infinity, this thing is going to e minus e, so this is infinity times infinity. We can rewrite this, as you know, divide this thing by this thing, okay? So then we have 1 plus 1 over x to the x minus e divided by 1 over x. I know this thing goes to 0, this thing goes to 0. We have a 0 over 0 indetermination, right? Now we want this change of variable, y equals 1 over x, because if we start differentiating these things, we're gonna get a lot of trouble, right? So we do the limit when y goes to 0 of 1 plus y to the 1 over y minus e divided by y. Okay, so again we have when y goes to 0, this is going to be e, because it's the same thing, and so e minus e divided by 0. And we can rewrite this expression, as we have done before previous problems, as e to the logarithm of 1 plus y over y minus e over y. And again, this is going to be 0 divided by 0, because the limit of the logarithm of 1 plus y over y when y goes to 0 is 1. Okay, this is one of those asymptotic equivalences that we know. So we can differentiate both numerator and denominator with respect to y, applying L'Hopital's rule. And so now we get rid of the denominator y, and so we have just the derivative of this, which is e to the, so again, e to the logarithm of 1 plus y divided by y times the derivative of this. Okay, and the derivative of this is 1 divided by y times 1 plus y, okay, the derivative of the first term, and then plus, in this case, it's minus 1 over y squared times the logarithm of 1 plus y. Okay, if it wants to appear. Okay, that's it, right? And so we can express everything in the same denominators. We have y squared 1 plus y, let's see, right? And then we have well, this limit, we can get rid of this, right? Because this is the limit of this times the limit of this, but the limit of this, we know this is going to be e, right? So you can write e here, e outside. And so then we have y minus, and then we have 1 plus y times the logarithm of 1 plus y, if I'm correct, right? And now let's see, we have, this is 0 minus 0 divided by 0 again, so we can apply well, sorry, we can get rid of the 1 plus y, because the limit, we can write this like this, the limit when y goes to 0, 1 plus y is 1, so this is y minus 1 plus y times the logarithm of 1 plus y divided by y squared, right? And then we can apply L'Hopital's rule again to this, because this is 0 over 0, so this e times the limit when y goes to 0, sorry, of, and then we have 2y, and then we have 1 minus, and then the derivative of this times this, which is the logarithm of 1 plus y, and minus, and let's see, and the derivative of the logarithm minus 1 plus y, which is 1. Okay, let's see, so we have 1 minus 1 minus this. Okay, so again, see this minus 1, sorry, 0 divided by 0. Again, we can apply L'Hopital's rule. Let me see if I can go back here. L'Hopital's rule here. So we have e times the limit when y goes to 0 of, and then we have minus, right, minus 1 over 1 plus y divided by 2. This is minus 1 divided by 2. The limit is going to be minus e over 2. Okay, this is the first limit. Okay. Let's do part 2. Part 2 is the limit when x goes to infinity of 1 plus 1 over x to the x squared over e to the x, right? And so now we don't really know how to compute this, because we know that 1 plus 1 over x to the x is e to the x, but yeah, we don't know how to deal with this. So one idea, and again, whenever you have exponents that are more complicated than x, you can always take the logarithm of this. Okay, so if we call this L, the logarithm of L is going to be the limit when x goes to infinity of, and then we have x squared times 1 plus 1 over x minus, and the logarithm of e to the x is x, right? And let's see, so we can divide, well, first of all, let me apply again the same change of variable as before. So we have the limit when y goes to 0, and we have 1 plus y divided by y squared minus 1 over y, and we can say this is y over y squared. This is the limit when y goes to 0 of 1, wait a minute, yeah, sorry, so this is not 1 plus 1, this is the logarithm of 1 plus 1 over x, yeah, so this is the logarithm of 1 plus y, and so we have the limit of the logarithm of 1 plus y minus y divided by y squared, and then we have this is 0 minus 0 divided by 0. We can apply L'Hopital's rule. This is the limit when y goes to 0 of 1 over 1 plus y minus 1 divided by 2y. Okay, and then we have 1 minus 1, 0 divided by 0, so we can apply L'Hopital's rule again, and we have the limit when y goes to 0 of minus 1 over 1 plus y squared divided by 2, and the limit of this is going to be minus 1 over 2. Okay, so the logarithm of L is minus 1 over 2. L is e to the minus 1 half. Okay, this is the limit that of u if you want 1 over the square root of e. Okay. Okay, let's do part 3. This is the limit when x goes to infinity of 2 to the 1 over x plus 18 to the 1 over x, sorry, 1 over x divided by 2 to the x. And if you try to substitute here, you get 2 to the 1 over x is going to go to 1 plus 1, 2 over 2. This is one of those 1 over infinity limits, and we know that they are of the case of the type e to the c, where this is the limit when x goes to 0 of, and then we have x times 2 to the 1 over x plus 18 to the 1 over x minus 2 over 2. And we can get this x dividing here, so this is 2 divided by x, and so now this is the limit of 1 plus 1 minus 2, which is 0 divided by 0. So again, we can apply L'Hopital's rule, but here before, again, we want to change the variable, so it's 2 to the y plus 18 to the y minus 2 divided by 2y. Okay, the limit is still 0 over 0, but this is easier to deal with, right? And so let me write it here. This is the limit when y goes to 0, and then we have the limit of the denominator. This is 2y logarithm of 2 plus 18 to the y logarithm of 18 divided by 2, right? If I'm correct. And so what we have is, let's see, when the limit when this goes to 0 is, this is 1 plus 1, so the limit of this is the logarithm of 2 times the logarithm, sorry, plus the logarithm of 18, which is the logarithm of 2 times 18 over 2. This is 36, so this is the logarithm of the square root of 36, the logarithm of 6. So c is the logarithm of 6, e to the c is e to the logarithm of 6. The limit is 6. Okay? And now let's go to the fourth one. And you can see that this fourth limit is just a generalization of the previous one, right? Because we have the sum of two terms divided by the number of terms we have to the 1 over x to the x, right? So this strategy is the same, right? This is one of those 1 to the infinity limit, okay, and this is equal to e to the c. C is the limit when x goes to infinity of let's see, x times, and then we have here in this here 1 over p times the sum from k equals 1 to p of a sub k to the 1 over x minus 1. We change the variable again, so we have the limit when y goes to 0 of 1 over p, the sum from k equals 1 to p of a sub k to the y minus 1 divided by y. Okay, and we can take the p here and p here. Okay, right? And now this is going to be p minus p0 divided by p. So this is the limit when y goes to 0 of, and then applying L'Hopital's rule, sorry, we have the sum of a to the k y times the logarithm of a sub k, sorry, to p divided by p. And this a k to the y, we're going to 1, so this is equal to the sum of the logarithm, let's write it here, the sum of the logarithm of a sub k over p, or in other words, logarithm of the product from k equals 1 to p of a sub k to the 1 over p. Okay, so the limit is going e to the c, so this is the limit is going to be the product from k equals 1 to p of a sub k to the 1 over p. Okay, this is the limit. And that ends the problem.